Welcome to Ask and Learn.
In this problem, we are talking about bond enthalpy. And this is a very important concept because this allows chemists to understand the energy difference between bonds breaking and bonds forming in reactions. So the way that we denote enthalpy is by delta H, and delta H is equivalent to the sum of the energy of the bonds broken minus the sum of the energy of the bonds formed. So another way you could say this is the sum of the reactants minus the sum of the products. And so we're given three reactions and we have to find the enthalpy of each reaction. So for our first reaction, we're given this alkene, this alkene, which if you don't know that word yet, that's okay. You'll learn that in organic chemistry. So we have this alkene and we're going to react it with H bound to 2 oxygen bound to another hydrogen. And this is what we call hydrogen peroxide. And we're going to form this compound where we basically just add these molecules into our alkene and get rid of that double bond. So how would we find the enthalpy? We have to use our knowledge of these bonds. So remember, it's the bonds broken minus the bonds that are formed. So our enthalpy would be 4 times the CH bond plus the carbon double bond plus 2 times our OH bond plus our oxygen-oxygen bond. We'll subtract our bonds formed, so we'll subtract 4 times our CH bond plus our carbon-carbon bond. Remember now this is just a single bond, plus 2 times a carbon-oxygen bond plus 2 times a hydrogen-oxygen bond. So now what you could do is you look in a enthalpy table and find the values of these exact bonds. These are known values. You don't have to do any calculations to find them. You can just find this bond in the table. It'll tell you. So now we'll plug that value into our equation for enthalpy. So we'll get 4 times 413 plus 614 plus 2 times 463 plus 146. We'll subtract off 4 times 413 plus 348 plus 2 times 358 plus 2 times 463. So now all you have to do is plug that into a calculator and you'll find that the enthalpy of this reaction based on the bonds is negative 304 kilojoules per mole. So now we can move on to our second reaction. This one is similar, but a little bit different because of our reagent. So now we have the same alkene, and we're going to add this molecule where we have a cyanide bond bound to a hydrogen. And what we're going to see is we're going to break that double bond in that carbon, and we'll just add on that cyanide bond to our organic molecule. So again, we can use the equation for enthalpy. Remember, bonds broken minus bonds formed. So our enthalpy will be equivalent to 5 times the CH bond plus the carbon double bond plus the carbon that is a triple bond to a nitrogen. That's the cyanide. We'll subtract 5 times the CH bond plus 2 times the carbon-carbon bond, now only with a single bond, and we'll add that C bound to a nitrogen with 3 bonds. Again, we can look these values up in a table. We'll get that delta H is 5 times 413 plus 614 plus 891. Then we'll subtract off 5 times 413 plus 2 times 348 plus 891. Again, you can just plug that into a calculator and we'll find that the enthalpy for this reaction is negative 82 kilojoules per mole. And now for our final reaction, this is a little bit different because now we don't have an organic molecule. We have 2 of these molecules of a nitrogen bound to 3 chlorines. And this is going to dissociate. We're not adding another reactant into diatomic nitrogen and diatomic chlorine. So the enthalpy equation for this will look like 6 times the NCl bond minus the diatomic nitrogen bond plus 3 times the diatomic chlorine bond. Then again, just look these up into a table. We'll get that our enthalpy is equivalent to 6 times 200 minus 941 plus 3 times 242. We'll plug that into a calculator, and we'll get that the enthalpy of our reaction is negative 467 kilojoules per mole. So I hope that this problem helped you understand, number one, how we can write reactions and understand the bonds that are forming and breaking in that reaction. And then we can use that information to find the enthalpy of our reaction, which is simply the energy that is moving or being released or absorbed in our reaction. And this is very important as a chemist because we can understand which reactions are energetically favorable.